So in last video, give you some review, some math notations we're gonna use during the class. And in this short video, we're gonna introduce the first classifier. It's called a linear classifier, right? So we're gonna introduce the linear decision function. A linear decision function is f. Your input is just a feature vector equals to a domain is a weight vector multiplied by inner product is x plus alpha. Alpha is a scalar. Okay. So here I will just give you one example. If d equals to 2, right? So this w is just the w1 and the w2. And this x is, oh, sorry. So inner product between w and the x is just the transpose of the w times x plus alpha, right? So this will be your decision function. We can simplify this a little bit. So this is just w1 x1 plus w2 x2 plus alpha. So this is your linear decision function. And recall that decision boundary we denote by h is a set of the x such that this equals to 0, right? Decision function equal to 0. Decision function equal to 0 is equivalent to say this w inner product is x equal to negative alpha. So why this is true? Because if we just set this equal to 0, okay, and we solve for x2. So w2 x2 will equals to negative w1 x1 minus alpha, and x2 will just equals to negative w1 over w2 x1 minus alpha over w2. Okay, so this decision boundary, this is our decision boundary h. So this is a line, okay? But if we have d greater than 2, this will be the hyperplane. And there is a theorem that x and y be 2 points on feature space, and it lies on decision boundary h. Okay, then w dot product is y minus x. Okay, if you have the decision boundary, remember the decision boundary is just a line, right? It's just a line. So suppose this is our decision boundary, and we have 2 points x and y here. Okay, so if we have 2 vector, one denoted by x, one denoted by y, y minus x is just denotes by the vector pointing from x to y. Okay, so this is just y minus x, and this theorem tells us the inner product between omega and this equals to 0. It's equal to 0. Actually, the proof is very simple. So the proof, this is because omega inner product with y minus x equals to omega inner product with y minus omega inner product with x. Because they both points are in the decision boundary, they both satisfies this equation. So this will equals to negative alpha. This one also equals to negative alpha, so negative alpha. So this will equals to 0. Remember, if two vectors inner product equal to 0, means these two vectors are perpendicular to each other, right? So we have, if this is x, this is y, then our w will so be perpendicular to our decision boundary. So in other words, given you the w vector, usually we're giving you a w vector, we can find the decision boundary this way. Okay, so therefore this tells us w is called normal vector of H. Okay, normal here means perpendicular to each other. Actually, there's a remark too. I'll give you a remark. If W is a unit vector, okay, then this fx equals to omega inner product with x plus alpha is a distance from x to h. It's just a distance between x to h. Okay, for example, if we have a point not living on the decision boundary, suppose this is the x here. Okay, so what's fx? So omega inner product with x plus alpha is just this distance. If it's above this decision boundary, so it's positive. If it's below, it's negative this distance. So it's the, I will use in different color here, signed. The distance between x and the decision boundary. Okay, so what's this alpha represents? So therefore, if you once you have the, suppose you have the xy plane, this is x1, x2. So suppose this is our decision boundary h. Actually, the alpha represents the distance between the origin and this decision boundary. Okay, so actually, so this implies the distance between h and origin is alpha. Here I just give you the example of a 2 dimension, but could be a d dimension. And this omega vector and alpha, we call it weights of a linear classifier. And another notation is called linear separable. So the training points linear separable. If there exists a hyperplane so in dimension if your feature dimension more than 3, you have the hyperplane. But if you just each feature has one dimension, 2 dimension, so it's just a line. There exists line that correctly classifies all the training points. Okay, in the next video, I'll give you one simple example of the linear classifier.